again, for this exponential function, I'm going to construct a table. Numbers, I'm going to try maybe these, again, for the x. And in this case, of course, I'm going to sketch this in try green. Green will work for me. So this says 1/2 raised to the -2, and I'll come back to it. This is 1/2 raised to a -1, come back to it. 1/2 raised to the 0, come back to it. 1/2 raised to the first. And 1/2 squared. Now 1/2 raised to a -2, guys, can someone tell me what you think 1/2 raised to a -2 has a value of? 4. What do you think 1/2 raised to a -1 is? 2. It just says take the reciprocal. 1/2 raised to the 0, of course that's 1. Anything raised to the 0 is 1. 1/2 raised to the first, no problem. Of course down here 1/4. Now this right here, guys, 1/2 raised to a -2. If you do it with a reciprocal and flip it over, make it 2, then square it. So if you see that negative sign, that says take the reciprocal, flip it over, and then square it. That's where the 4 came from. Now if I plot those, I'm going to plot it on the same grid up there and hope it'll work for me. It says -2 up 4. Well, that's up here. -1 up 2, somewhere in there. 0 up 1, I'll just share a point. Out 1 up 1/2, that's right in there. And out 2 up 1/4, barely above the x-axis, it's 1/4. Connect those in the green, and it looks like it's going to look something like this. That's the graph of the 1/2 raised to the x. The red one was the graph of this. And they're both exponential functions. Just basic exponential functions. Is there a relationship between the two?
Yeah.
Like what?
It's a reverse.
Well, don't use the word reverse.
Reflection across.
Is there a reflection across the
y-axis?
y-axis? Now you say, Professor, looks like maybe if you take that red graph and reflect it across the y, here's the y, might it turn into the green? A reflection across the y-axis. And the reason is, the way I have this written, everyone in class would agree that 1/2 raised to the x could be, if I wish, written like that. Is 2 raised to the -x the same as this?
Yeah.
And now what's that negative sign say to do there at the top? It says take your 2 raised to the x graph, like your parent graph, and reflect it through the y-axis. That's why you get that reflection there. So guys, that's what exponentials will do for us here shortly. Now, with that said, if I'm ready for it, I am. Then we'll stop here. Find this. Oh, right here. Now, Mr. Park, I've got to do this with the time before that quiz starts. We're going to do something. Mr. Park has gone through this. He's already just completed a math competition. Right, Mr. Park?
Yeah.
He feels good about it. He's going to win the $500. Now, since he's already gone through it, he'll know, and I'll let you know now for Math 2, you guys are going on into Math 7, there is a base on these exponential functions. I used 2 for my example. It could be 3, as long as it meets this constraint. It could be 4 raised to the x. It could be 1/4 raised to the x. And you graph it, and graph it, and graph it, and graph it, and graph it. The one that the calc and everything above calc that they love for the base is a number that you have not in my class, you have never witnessed. But they love it for a reason, for the base. Now, Mr. Park, he's going to help me. First, I'm gonna show you where this number came from and then what we name it as. I'm gonna do a table. I'll label one side X, the other side as this. 1 plus 1 over X raised to the X. Oh, it's a math class. What do you think we're gonna do? Stick with quadratics all semester? No. Now, what I want to do is, I'm gonna try to come up with this number that's used so often for the base, exponential. I'm going to come up with, and I think I did, I sure did, some numbers. I started out with a 10 for a reason. Now I jumped to 100, 1,000, 10,000, 100,000. And I may even ask him to try 1 million. But he's going to help me, he sort of knows where I'm going. Those are my selected numbers in that X column. Can someone tell me, in terms of a, how can I say it, assemble something to show what am I showing in that X column? And give me maybe some notation to indicate what is Ramsey trying to indicate in that column there with those numbers, yes? There we go. Oh, not scientific notation, something else. Something else that would fall right in line with what something we just did. No, something else. I started with a 10, then I jumped to 100. Then I jumped to 1,000. 10,000. So what might you say Ramsey's trying to show? Because I could go to 1 million, 10 million in that left-hand column. What am I trying to show? The X is doing what? It's approaching infinity. I'm trying to make the X get large and large and large and large. I stopped at 100,000. Now, my concern is to get this particular number they love for the base is what on earth, and where did this come from, Professor? What on earth is this expression getting close to? If I plug in those red numbers, Mr. Park, hang on, you're going to help me. So this is 1 plus 1/10 raised to the 10th if I plug in the 10. Mr. Park, give me a second, I need some help. Why don't you think of that as 1.1 and raise it to the 10th and tell me to 4 decimal places, what is that approximately equal to?
2.5937.
I'll carry it up there. Now he's doing the math for me. Now we'll jump down, same expression, and put in 100. Mr. Park, can you tell me what on earth is that close to?
2.7048.
Let's try 1,000. Raised to 1,000. Tell me what that's close to.
2.7169.
2.7145?
169.
165.
Yeah.
Okay, I'm gonna try 10,000. Big numbers been raised to big numbers. What's that?
2.7181.
1. Try 100,000.
2.718.
Oh, hang on. You said it's close to what?
2.7183.
Oh. Let's try one more. 1 million.
Okay.
I'll go ahead and just ask you what it is. What's that close to?
2.7183.
Really?
Yeah.
Really? What do you think, as I make X get large, which could be written as X is approaching infinity, what do you think this side it's getting close to with the values he gave me. As I plugged in those large numbers into this crazy expression, what do you think those numbers are getting close to? 2.718 to 3 decimal places. Are they getting close to 2.718? I bet if I ask him to try 10 million, it's going to be close to 2.718 again. Starts getting stable right around that number. So guys, this is approximately 2.718. You'll say, Professor, my goodness, okay, I'm going to put the approximate symbol here. It's 2.718. We accept that as the approximate value for, and they identify this as a number. They call this number E. Not pi. Pi is roughly 3.14. They call this number E, and they love, and you'll find out why they love in the higher math courses, E raised to the x, E raised to the x, E raised to the x. And this is where E came from, that number. So it's roughly 2.718 for its value. And you write down something, I'll take questions here. Conclusion, write this as, if I find the limit as x is getting large of this expression, as Mr. Park helped me, we identify that as E. That's exactly what this table says. I made the x get large, in other words, x is approaching infinity. What's the limit of the other side? 1 plus 1 for x raised to the x. It's getting close to this number, which we identify as E. E is roughly 2.718.
What about if it approaches the infinity? It's going to be the same number.
Same. No, hang on. Are you saying maybe E raised to the negative x? That would be 1 over E. It's going to be a reciprocal. Okay, I want positive infinity. Guys, at least you'll know when you see E, and you'll start seeing E in this textbook quite often. And in calculus, math 7, math 8, you'll see lots of E's. Lots of E's. Is that true, Mr. Park? They deal with lots of E's as a base in calc. Okay? Not 2 raised to the x. I like 2 raised to the x myself. Not 3 raised to the x. E raised to the x. And they give you a rationale why they like E raised to the x, which I could go into, but they like to do that for a reason for the higher math. Now, I'd like to, with your help, if we accept this as E, I'd like to now sketch, look at this, f of x is equal to, not 2 raised to the x, I did that before the break, not 1/2 raised to the x, E raised to the x. We have a new number. Now let's try to graph that exponential function. And use the base. By the way, the restriction on the base was a must be greater than 0, and don't let a be 1. But E certainly meets those conditions. Now what would that look like as a graph? Guys, I formed a table before the break to see what 2 raised to the x and 3 raised to the x, not 3 raised to the x, 2 raised to the x and 1/2 raised to the x look like. Now, so you'll be ready for me on Monday. Just quickly, with your help, go to a grid. I'm trying to graph E raised to the x and see what the shape of the graph looks like. I'm going to, since I did this before the break, I'm going to first sketch 2 raised to the x. I think I did that before the break, didn't I? Did I sketch 2 raised to the x or not? I did, didn't I? Yeah. 2 raised to the x? 2 raised to the x, guys, remind me somehow, what did it look like? Before the break, what did 2 raised to the x look like? And I'll just place it real quick without going through another table. Did it look like this? No? Like this?
Yeah.
So it did something like this. And it went through, I think, 1, didn't it?
Yeah.
For y-intercept, right here. This is 0, 1, and that's what 2 raised to the x before the break looked like. Now, without going through a table, I don't know why I better go through a table. I like to graph in red, I get to the grid, this function for a reason. I like to see what 3 raised to the x looks like. And then we'll use the same numbers in that x column. And here we go, guys. This is 3 raised to a negative 2, 3 raised to a negative 1, 3 raised to 0, 3 raised to 1, 3 squared. Values from elementary school, 1/9, 1/3, 1, 3, 9. I like to plot those. Plot those in red, same grid. Negative 2 goes up to 1/9. I had better mark a few numbers here so I can see where I am. Negative 2 goes up to 1/9. That means it's barely above the x-axis. Right there. Negative 1 goes up to 1/3. Looks like it might be good a little higher. 0 finally gets up to 1 from that table. 1 goes up to 3. I'm going to mark 3 and be ready for it. 1, 2, 3. I think the last one goes up to 9. I'm going to put it up there, guys. Okay, 1, 2, 3. We'll put my 3 there. Let's go back 0, 1. I got that one out of the way. The next one's 1, 3 in here. And finally, if all is correct, 2 goes up to 9. Is that true? Connect those in the red. Close to the x-axis. I mean, really close. There's 3 raised to the x. I got 2 raised to the x, 3 raised to the x. You see the difference in the graph? One is steeper than the other. And then you see other characteristics of those 2 graphs. 2 raised to the x in the black, 3 raised to the x in red. If I applied all those correctly, which I think it did. Now, where do you think e raised to the x fits between the 2? E is roughly 2.718. Is that caught between 2 and 3?
Yeah.
So that means if I want to, another note, not a table, show the best I can what this might look like, I would have to be patient and squeeze it in somewhere in here, in between the 2, and I'll call that a basic shape of e raised to the x. Squeezed in between those 2 graphs, which I think I did. And that's a graph of e raised to the x. Jeez. Check my time here. Got plenty of time. Are we okay here, guys? Now, when you see me on Monday, chapter 4 will finish. In fact, we'll probably have time at the end of the class on Monday to start chapter 5. Sure.
For the next quiz, it's going to be composites.
It's going to be I'll give you a little handout. Get ready for it. That's going to be composites and inverses. Yes. Okay? Guys, let's have everything put away. I made this quiz what I consider a short